Anyways, it's fixed now. Hopefully that'll help you. And let's go ahead and get started. If you look at chapter 25, it's called Electric Current and Resistance, and it starts off with a photograph, or a photograph. Obviously, it's not a photograph. Start off with a painting of Alessandro Volta introducing his battery that he invented to Napoleon. Not to be confused with Napoleon Dynamite. That's a different character. But that was in 1801. So, anyways, what it started off with was Luigi Galvani at the University of Bologna had discovered that basically when he was messing with frog cadavers, basically he'd find that their muscles would contract. And in fact, for some period, they thought it might be they were finally discovering the life force, i.e., the soul. Of course, we've come quite a different way since then. A lot of people say that we don't believe animals have souls and stuff like that, so who knows? But the main thing is we ultimately determined it wasn't souls that was making the frog's legs twitch. It was actually dissimilar metals. So if you let two different metals get in a moist area like the a thigh muscle, for instance, of a frog, even if it's a dead frog, then electric voltage will or electric potential difference will be generated between the two metals, and that causes a contraction of the muscle. So Alessandro Volta was one of the people that helped figure it out that was just dissimilar metals. So he created a battery, and you can look. It's got a diagram of the battery. It's just a stack of. I think in this case they went with silver and zinc, but any two dissimilar metals will work just fine. The one I do with my students, I shouldn't say my students, but when I used to do demonstrations at Port Discover in Elizabeth City, I would do it with lemons, but you can do it with potatoes, lemons, apples, oranges, just about anything, long as you have some kind of fluid inside of it that can carry ions, which means basically everything but distilled water, and probably distilled water, if you left it there long enough, it could do it as well. But mainly any of that kind of liquid, vinegar would work, an acid would work, a base would work, regular water would work if, like I said, if it's not deionized or distilled, it should work. But I would take at my students, and we normally would buy a bunch of lemons, and you could take and buy some copper wire, like some number zero or number eight wire or number two wire or something like that, with no housing on it, and in other words, no insulative coating. And I'd stab that in one end of a lemon, and then I'd take a galvanized nail and stab it in the other end of a lemon, and you could take a voltmeter and put it across it, and it would read, depending on various parameters, it would read anywhere from zero point 0.2 to zero point 0.8 volts, just from two different metals in one lemon. But then you could take the zinc nail and wire that up to the copper wire of another lemon, and then measure the difference between the zinc of the second lemon and the copper of the first lemon. And if you got zero point 0.4 volts the first time, now you're going to get zero point 0.8 volts going on across two. And it sort of does that for a while. If you add three, it's three times what the voltage of one was. If you add four, it's four times. But eventually it gets to the point where the returns are diminishing. So you're not, increasing it by the same amount every time, but still you can get it up quite high. So that's a way you can make one in everyday life. I usually tell my students you can also use, for instance, a zinc washer, and you throw it in the bottom of a prescription bottle with the wires soldered to the bottom of that zinc washer, and have the wire sticking up out of the prescription bottle. And then I normally put like a little piece of gauze down, and then I put a copper penny, which is just copper coated, of course. Put a copper penny on top of that, and if you soldered a wire to the top of that penny, and then you filled in the actual prescription bottle with like lemonade or vinegar or something like that, or even just water, really, then what you measure is a little voltage difference between the top side of the penny and the bottom side of the zinc washer. If you instead pulled that penny out, put another penny there, put another piece of gauze, put another piece of zinc washer, and then put the penny on top, you get twice as much voltage, and you can keep doing that. So that's another good way. Or, as your book shows, you put one carbon rod and one zinc rod into sulfuric acid solution. The carbon will lose electrons, and the zinc will collect them. So that makes the carbon turn out to be the positive terminal, and the zinc turn out to be the negative terminal. And that's more or less the way modern batteries like AA, AAA C and D batteries are actually made, except they use, you've probably heard they're called alkaline batteries, so they're not using an acidic solution, they're using an alkaline solution. If you open one up, or at least the last time I opened one up, and it's not safe to do this, so I do not recommend doing it. I just know that I'm an idiot and I did it when I was young and didn't know any better, but I opened it up, and what I found inside was some paste that actually is quite irritating to the skin, so that's kind of nice. But then I found just basically a little vein of carbon down the middle. I didn't at that time know that was carbon, but in retrospect, you can tell because it's just like black dust sort of stuff. And then the outside container that's like a little cup that makes the negative terminal of the battery, and that's the bottom of the battery. And then the carbon rod comes out the top, and they have a little piece of metal that's insulated away from the zinc part of the cup in the at the bottom, and that touches the carbon rod at top, and that makes the positive terminal of the battery. So that's how a modern battery is made. I've drawn the symbols for batteries up here at the top left. The easiest one to draw is just one long rod with one short rod, or one long bar with one short bar. The long bar represents the positive terminal, and the short bar represents the negative terminal. And then it's just a wire coming from both of them. I have seen, for instance, many diagrams will use the number of lines in your battery diagram as indicative of a certain amount of voltage. So, for instance, when I looked at Chitten's manual for my F350, I discovered it had a set of 24 lines. So short line, long line, that's two, short line, long line, that's four, and it went all the way up to 12. And what I realized was that each two lines counted as 2 volts because my truck batteries actually for my truck is a 24 volt battery, not a 12 volt battery because it's a big diesel engine. And in that sense, when you look at the wiring diagram, it's got literally 12 of those stacked up, and that's an indicator of what the voltage is. So in electronics, at least in certain branches of electronics and electrical engineering, they'll use that as a measure of the actual voltage. And it looks like things are stacked on top of each other or piled on top of each other, and that's where we get the phrase battery, as if it's a collection, or the phrase pile, as in the nuclear reactor that we had under the football stadium at University of Chicago was called a pile, and so on and so forth. But with that in mind, I just want to let you know that's actually how you go about making a battery. We're going to work with that. We're going to define current. We're going to use Ohm's law. We're going to tell you how the resistance depends on the geometry of the material through which a current's pushed, and stuff of that way, of that nature. And we're also going to tell you how that resistance will change as a function of which material you're on, as well as a function of temperature. So I thought I'd get started by just working some examples and giving you the information that we need as we go along. So I've now explained the battery. I want to explain a little bit about a circuit because that's what they talk about a little bit in section 25.1 and 25.2. They show you various diagrams with wires and batteries and light bulbs. So the one thing I want to mention to you is that when you're dealing with a light bulb, like this one, for instance, there's the threads, and then if you look at the bottom, you can see there's a sort of dull metallic stuff in the middle, and then there's a shiny black part around the outside. That shiny black part is some kind of insulator that isolates that dull gray stuff in the middle from this aluminum on the outside where the threads are. If you were to open this up, what you'd find out is a wire is more or less soldered to the threads, and then it goes up and makes a little coil, and then the other end of the wire comes down and is soldered to the bottom of this little silver thing, and that's the way light bulbs are wired. So what you recognize with a light bulb, and they're normally, I've never seen one that requires it to be put in a specific direction. So you can run the current in the threads and out the bottom, or you can run it in the bottom and out the threads with every one I've ever seen. But I'm sure someone makes one that's polar, but I just haven't ran into it. And normally the wire, by the way, is made of tungsten, which is dirt cheap, can get really hot without melting, and doesn't oxidize that easy. It doesn't corrode very easily. So it just happens to be a pretty nice material for doing that. And when you run the current through it, it's not that good of a conductor, so it tends to get quite a bit hot when current's running through it, as opposed to just letting it run through without getting very hot. And once it reaches somewhere around 2500 degrees Celsius, then 2,000, 2,500. I haven't done that calculation in a while, but it's in the ballpark of that. I just want you to know it's on the order of thousands of degrees. Once it reaches that temperature, then it steps into the visible part of the spectrum, and we see a little bit of red, which you guys saw in your Ohm's Law lab and maybe even your series and parallel circuits labs. If you go hotter and hotter, that red goes from, across the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, until it becomes more or less white hot. And what's going on there is all the colors are being represented. If you learned anything about colors of light, you'd know that the primary colors, when you add them together, make white, which is different from paint. When you do paint, all the three primary colors go together, you get what's called mud. And depending on the percentages, it could be like a brown or a gray, or something like that. But when you mix the three primary colors, or all the colors in general, you get white light when you're talking about mixing light. So another part that they want to talk about is, in addition to how we get the power, and of course I just told you how a light bulb works, or at least the incandescent light bulb works. If you wanted to know about how circuits work, you have to think about the idea of what a circuit is. A circuit carries what we call conventional current, and conventional current is the idea that little positive particles are running away from the positive terminals of batteries and running towards the negative terminals of batteries. And we even look at it like the positive charges are coming out of the positive terminal of the battery and then going through the wire and then running into the load or loads and then coming out of the load and going back into the negative terminal of the battery. It's not really doing that. More or less, what you're looking at is the wire actually has, being a conductor, it doesn't hold on to all of its electrons really well. That's the nature of a conductor. An insulator, on the other hand, holds pretty strongly onto all of its electrons so that the electrons more or less stay with their parent atom. But when you have conductors, or if you have a voltage situation or electric field situation that's so strong that those electrons can break free from their atoms, then the object is acting like a conductor as opposed to an insulator. So what really happens is, if you take a piece of wire and you connect it to the positive terminal of a battery and then you run it into a load, the positive side of the load if it has one, and then run another piece of wire from the negative side of the load to the negative side of the battery, the wire has free electrons that are willing to move inside of it. And when you connect the battery to it, the positive terminal of the battery repels the positive charges, but they can't move. So what really happens is the negative terminal of the battery repels the negative charges, and the negative charges act more like they're coming out of the negative terminal of the battery and then entering the negative side of the load and then coming out the positive side of the load and then going back in the positive side of the battery. So whenever you go to wire something, you should be thinking in terms of that, not necessarily the negative side, but you can pretend the positive side, because that's what we really talk about day in and day out. We had a choice in the era of Ben Franklin, and Ben Franklin's the one that gave us the idea of using positive charges and negative charges, and he had like a 50-50 chance of choosing it in such a way that positive particles were going around, but what he chose was exactly the opposite. So now we pretend like positive charges are running away from the positive terminal of the battery, going through the load, and then attracted to the negative terminal, when in reality it's actually negative charges running from the negative terminal of the battery, going through the load, and then coming back to the positive terminal of the battery. In neither case are they actually exiting the battery and entering the battery. It's more like they're just being compelled to move in that direction. Uh, but as luck would have it, it turns out that unless you're studying the difference in voltage from the top edge to the bottom edge, or from the right edge to the left edge, or from this edge to this edge, or this edge to this edge of a wire, unless you're measuring the voltage difference between those two pieces of wire while a magnetic field is acting perpendicular to the wire and currents going through it, unless you're doing that, you really can't tell whether it's positive charges going around this way or negative charges going around that way. That effect is called the Hall effect, and we'll study that eventually. It's just a matter of letting you know that you're not going to lose any points or get any problems wrong by assuming positive charges are leaving the positive terminal of the battery and entering the negative terminal of the battery, even though reality is that the negative particles, the electrons, are running from the negative terminal and running towards the positive terminal. So it's good to know what the reality is, but it's also good to know that we can still pretend like conventional current is the reality and solve physics problems and get right answers. So again, think about that. Think, do I have a complete path for, again, just imagining positive particles leaving the battery through the positive terminal, going through the load, and then bringing those positive particles back in through the negative side of the battery. You can do it the other way around with regular current instead of conventional current. But the main thing is you've got to have that exit and a path and then that entrance. If you don't have all those parts to the circuit, it's not going to be a complete circuit. And that's part of what your textbook is doing by showing you these various diagrams of how to wire batteries together, how to wire batteries to light bulbs, and how to, for instance, one of the examples, it tells you how to connect a battery to a light bulb with only one wire. And it asks you to figure out what's wrong with each of the scenarios and which one actually isn't wrong and which one will actually work. So that should cover that. Now that I've discussed the battery, I've discussed how the charges flow around, and I should mention I haven't said this yet, even though I've said it probably in previous classes. That charge flowing around, which we treat as conventional charge, positive particles flowing, if you were to count the number of coulombs that went past a certain part of the wire every second, then you would be calculating the average current. Current is coulombs per unit time. So if you, as I said, were like an eyeball watching this one spot of in a circuit, and you were counting the number of coulombs that went by, and you counted all those coulombs, positive, 54 or whatever, and that happened in 1 second, then you would have 54 coulombs per second, which is the same thing as 54 amps. In reality, you can call that the average current is delta Q for change in charge over delta T for change in time. And that would be the average current, if you will. But if you wanted the instantaneous current, it's just like switching from the average velocity to the instantaneous velocity. You'd take the limit as delta T approaches zero of delta Q over delta T, and that becomes dQ dt. So that gives us a couple of equations to work with, and we can now go on to solving some examples. So I've now gone through the parts of a light bulb. I've mentioned how you can picture whether wires will work. I highly recommend you be responsible for all the subsections within chapter 25. Let me tell you which ones I'm skipping. Subsection 25.9 on superconductivity and subsection 25.10 on electrical conduction and the human nervous system. Both of those are very interesting, and I highly recommend you read them. But any examples in there, which I don't think there are any, are not your responsibility. I'm not going to ask you questions from that, but you will learn a lot by reading all it. So I do highly recommend you read it. Now we'll go ahead on into section 25.2 so we can do some examples. Maybe I'm trying to turn the book ahead and it's going very, very slowly. Okay, so what we've found so far is that on average, I average is equal to delta Q over delta T. So that's the normal scenario. That's a way you can calculate current. And if your delta T is small enough, average current and instantaneous current are the same thing. But if you want to find I instantaneous, which I'll just call plain I from here on out, then you take the limit as delta T approaches zero of delta Q over delta T. And of course, you know from calculus that that is dQ dt. Okay, so that's two of the equations we're going to use. I will tell you that the units are the dimensions depending on what you want to work on, but I'm going to work on units. The units of current are the units of charge divided by the units of time. And of course, the unit of charge is the coulomb, and the unit of time is the second. And I want you to know that 1 coulomb per second is defined to be 1 ampere, named after a person whose last name is Ampere. And the abbreviation for that is a capital A. So that's the amp. An amp is a buttload of current. It can do a lot of damage to a human being. It in fact it only takes a milliamp to kill a human. So if you actually put even as small current as a milliamp across the heart, you can in principle kill a human for that. So current's the thing you really most watch out for. You don't want the current running across your extreme from one extremity to the other through your heart or anything like that. Obviously, current going through your skull would be problematic for your brain and tissues, and obviously, any of that going through there could cause burning, all sorts of stuff like that. But the main point of all this is one, letting you know about the safety, that current's the issue, not the voltage. You can, for instance, there's a lot of systems that I interact with. For instance, the Van de Graaff accelerator or the Van de Graaff demonstration tool that you've seen in museums and TV and stuff like that. It's a big silver ball that sits on top of a pole, and you'll see a lady will grab it, and her long hair will stand straight up. That's a Van de Graaff, and that device more or less is just an electric motor at the bottom that spins a long, wide rubber band. So it's like a rubber band that's like 2 inches in width, and the rubber band goes from a little Teflon spool at the bottom up to another Teflon spool at the top, and the motor at the bottom of the Van de Graaff causes the Teflon pulley at the bottom or the spool at the bottom to rotate. That actually turns the rubber band and causes the rubber band to go up inside the sphere on top, go around the little spool up there, and then come back down. As it does that, just the brief time that the rubber is in contact with the Teflon, the rubber has a little bit more affinity for the electrons than does the Teflon. And I'm imagining this, I haven't confirmed that it's definitely Teflon has a lower or a lower attraction for electrons than does rubber. I'm just trying to use a concrete model so you'd understand. But there's ways to look up that to figure out which one wins in such a battle, and that's how we, discovered, for instance, when you rub fur against a piece of plexiglass, which one gets the electrons, which one loses electrons. That's all about the affinity that the individual substances have for the electrons. So I'm just telling you there is a way to do that, but I'm pretending right now because I don't know off the top of my head whether it's the rubber band taking electrons. I suspect it is from the Teflon or not. But the main thing is the in separating the rubber band from the Teflon as it leaves the spool, some of the electrons jump off of the Teflon and onto the rubber band. They therefore ride up the rubber band, which is an insulator, so it's the electrons aren't free to move. They ride up the rubber band, and then when they get to the top spool, inside of the metal sphere is something that looks like a screen patch. It's about this big, or it's actually quite a bit smaller than that. It's maybe 2 inches wide by an inch and a half tall, and it's more or less a two-dimensional, really shiny stainless steel screen. So it's interwoven, like a woven basket or something like that. But the ends of the individual screen just come out as little points, so they don't actually have, any kind of frame around it. It's just the points, and those points are acting like lightning rods, so that the actual negative charges say, "Hey, that's a difference in voltage between me here on this rubber band and you, that metal over there." So it jumps to that little lightning rod, and then that lightning rod, which is part of a screen, that screen is connected to a copper wire that's connected to the inside of the aluminum disc that's on top of the Van de Graaff, and therefore the negative charges run out through that wire, through the screen first, and then through the wire, and then they locate themselves on the outside surface of the sphere that you see at the top. When you do that, you can actually get on the order of 10,000 to 50,000 volts, but you can tell by the way of how it works. That's part of the reason why I explained that to you. The way that it works, you're not going to get a lot of electrons to come up that way. So Electrons are, 1.602 times 10 to the negative 19th coulombs per electron. So you're not going to get a ton of coulombs coming to the head of the Van de Graaff either, and therefore you're relatively, and again I say relatively, if you screw up things or get in a water situation, jump in a tub or something stupid like that, it will definitely kill you. But I do a lot of stuff with the Van de Graaff where I let the lightning jump off the Van de Graaff and through my knuckles, and I see it shoot out my toes and out the side of my shoes and stuff like that. So in that case, even though I've got a high voltage, it's because I have a low current that I'm safe. Okay, so I don't recommend you experimenting and trying to find out what you can handle because I've gotten hurt several times with electricity, mainly because of my curiosity. So I do not recommend you do any of that. But still, the big thing to remember is current is what kills you. The voltage can be very high and possibly kill you, but the voltage can also be very low and possibly kill you. So it's more about the current that you worry about and the ability to drive a large number of coulombs per second. As I said, the ampere is the unit of current, but we're more often using milliamps and microamps and stuff like that, unless you're dealing with some, really big circuitry with a lot of voltage. For instance, a typical house has a 200 amp service. So if you build a house out in some community or whatever, the power company will come and connect you with electricity, and their standard is that they normally connect you with a 200 amp supply. So that means your house can run up to 200 amps with no problems. If you need more than that, there's processes you can go through to have Dominion Power or whoever your power company is give you more than a 200 amp service. But it comes in oddly enough at 120 AC, but it's what we call triphasic. So there's a sine wave, and then 60 degrees later there's another sine wave, and then 60 degrees later from that one's another sine wave. And because of that triphasic, none of them have a peak voltage any higher than square root of 2 times 120-ish volts. But because they're offset, if you take the peak of the first sine wave with the trough of the third sine wave, you'll find that difference is basically 120 plus 120. So you end up getting what we call 240. Again, that's 240, which is technically the root mean square voltage, just like the 120 is the root mean square voltage. But that's what comes into your house, at least in America. So we have the ability to run 240 volts. That's what your dryer and your stove will run on, but most of the stuff in the house is going to run on the 120. And they can do it without ever sending anything as high as an actual 240 volts. They're only sending in something that has a root mean square of around 120, 125 volts. But because it's three different phases and you can align the peak up with the trough, you get a difference of voltage from the top being whatever 120 times the square root of 2 is, all the way down to negative 120 times the square root of 2. That's the peak to peak. And you'll find that that's actually 240 times the square root of 2. But we call the single phase 120, and we call the double phase, or the across three phases, we call that 240. So just keep that in mind. Now we'll move on, since I've told you about this stuff, and I'm going to do example 25.1. Example 25.1 says a steady current of 2.5 amps exists in a wire for 4 minutes. A, how much total charge passes by a given point in the circuit during those 4 minutes? And B, how many electrons would this be? So I'm going to go ahead and solve this right here. I've got plenty of room down here at the bottom, and this is example. I hate that. Does it every time. 25. 1, what we have is I is equal to 2.5 amps, and delta T is equal to 4.0 minutes. And of course, we're going to need that in seconds. So 1 minute is 60 seconds. 4 times 60 is 240. So this is 240 seconds. And what we want to know for part A is how much total charge, delta Q, passes during that time. And then in part B, they want to know the number of electrons that passes by in that 4 minutes. Okay. So what we're going to use is solution I bar is equal to delta Q over delta T. And we're also going to use the fact that the charge for an electron, which is given the symbol E, and I'm talking magnitude here. Everybody knows an electron is negative, but I'm just going to give you the magnitude of it. It's 1.602 times 10 to the negative 19th coulombs. And when you're doing things like calculating the number of electrons, it's best to think about this as not just coulombs, but coulombs per E minus. So coulombs per electron, in other words. Okay, so I'll use that. Now for part A, they want to know delta Q, and according to I bar equals delta Q over delta Q would be equal to I bar times delta T. And of course, I bar is 2.5 amps, which is coulombs per second, and delta T is 240 seconds. Now, 2 times 240 is 480, and then zero point 0.5 of 240 is 120. So 120 plus 480 would be 600. So this gives us 600 coulombs of charge is equal to the amount of charge that goes by a single spot in the circuit over that 4 minute period. So 600 coulombs. And remember, a coulomb is a big unit. It's not unreasonable to find a lightning strike carrying only around 100 coulombs. So 600 coulombs is a pretty big deal. Now we'll go to part B. And part B is the number of electrons. So the number of electrons, which I'll write as number E minuses, like that, uh, the number of electrons can be delta Q divided by the charge per electron. So in this case, what I'm going to do is I'm going to take 600 coulombs and divide it by 1.602 times 10 to the negative 19th coulombs per E minus. And this is where you see by using it as coulombs per electron minus per E minus, you'll see that I end up getting units of E minuses. So that gives you a little bit of confirmation that, oh, I did it the right way. If I did, you might have thought maybe I multiply 1.602 times 10 to the negative 19th times the 600, or maybe you thought you'd take the 1.602 times 10 to the negative 19th and divide it by the 600. This definitively gives you a way of calculating it, and it come out in units that seem reasonable, so you know that you did it correctly. So doing that, I'm going to take 600 and divide it by 1.602 times 10 to the negative 19th. Now, obviously, we really don't need 4 sig figs on this. In fact, it's probably not even useful to have more than one. But since we use 2 everywhere, I'm going to go ahead and give it to you in 2 sig figs with 1 extra. So when I divide the 600 coulombs by 1.602 times 10 to the negative 19th coulombs per electron, I get 3.7 5 times 10 to the 21st E minuses. So that's the actual answer for the number of E minuses. Anybody have any questions on that? Yeah, this stuff should be pretty straightforward. So I don't expect necessarily asking questions, but I want you to ask them if you have any reason to ask them. So let's move on to example 25.2. This is one where they're talking about, it's actually a conceptual example, and they ask you specifically what is wrong with each scheme shown in figure 25.7 for lighting a flashlight bulb with a flashlight battery and a single wire. So here it is, how to connect a battery. What is wrong with each of the schemes shown in figure 25.7 for lighting a flashlight bulb with a flashlight battery and a single wire? So remember my story I told you got to think about when you're trying to run wire is you got to think, hey, I have a positive source of positive particles that positive particles have to be able to come out of and then run through the load and then come out of the load and run back into the negative side of our power source. That's what tells you you've got everything wired correctly. So if you look at this top diagram, you see the positive terminal is up here. So you can imagine positive particles. Again, they don't necessarily leave the battery, but for argument's sake and for model's sake, it's certainly fine to pretend they do. But you can imagine the positive particles coming out here, going down the wire, and then entering through that terminal in the bottom of the light bulb that I told you about. But you see nowhere for the particles to return back to the negative side. So that's what's wrong with part A. If I do it with part B, you look like, oh, well, now they're using both terminals of the battery. They got one end of the wires touching the bottom center, like I told you, and the other end of the wires touching the threads. That's the other terminal. But in this case, if you imagine the positive particles coming out of the positive terminal of the battery, they're either going to go in the threads and then come back to the positive terminal, which isn't helpful, or they're going to go out of the positive terminal in through the bottom and then out the threads and back to the positive terminal. So that one's not helpful either. If you look at this last one, though, you can see that positive particles could come out of the positive end of the battery, go into the bottom of the light bulb, go through that little tungsten wire, do the little loop-to-loop, and then come out the threads. When it comes out the threads, then it could follow this wire and go back in the negative terminal of the battery. So yes, example C is a proper wiring, is a way that you could properly wire to get the light bulb to work. So I want you guys to think at that microscopic level when you try to connect circuits with wires and batteries and power sources. When you get to AC, it's a little different, but it's still sort of the same thing. At least at each phase, AC goes 0 to a peak, which is like 120 times the square root of 2, and then back to 0. That's one whole positive increment. So in that case, that part of the AC curve, that's all stuff going, say, from left to right. But then it goes from 0 to negative square root of 2 times 120, and then back up to 0. In that particular portion of the AC, it's actually going from left to right instead of right to left, or vice versa, whichever one. So the top part's going, say, right to left, the bottom part's going left to right, and at least for that half cycle, you can still picture it just like this. So that's the way you can still make sense of circuits when you're dealing with AC. Is just think about one terminal. Now, when you look at the wires for AC, they normally have a black wire, white wire, and then a clean wire, a wire with no housing. It's normally just gold. Sometimes they'll have a fourth one that's like a green or a brown or something like that. But the black wire is supposed to be the source. That's where the AC voltage or AC current comes out. The white is supposed to be a neutral, so it can act like a route to let those charges go back through. And then the ground is something extra that we've discovered is extremely helpful, because if you can have a ground available at each circuit, if you actually overload it, instead of it sending all that electricity out to try to find the nearest ground, which might be, through your heart or through your daughter or son or something terrible like that, then it will automatically find the ground that's right there in the circuit and send it safely away. That's why we have these weird light receptacles that you find, for instance, in bathrooms and around kitchen sinks and stuff like that, that have little buttons on them. They're called GFCIs, which are ground fault circuit interrupts. And basically, they have a mechanism inside of them that detects when the current gets really, really big, which is what happens when you have a basically an overload of a circuit or too small of a resistance or something like that. When you have that, then the current starts running really, really high. And what the ground fault circuit interrupt does is it says, oh, I see this current's getting really high. Let me really quickly, and I'm talking like on the order of milliseconds or microseconds, it will immediately take all the current and run it straight to the ground. And that, of course, makes it safe. In principle, again, do not try this stuff, but in principle, you could be able to supposedly take, for instance, a space heater or a hair dryer or something that would kill you if you jumped in a bathtub with it, and you could jump in a bathtub with it plugged into a GFCI, and if the GFCI is working properly, it will protect you so rapidly that you won't even feel a sting or anything. Again, do not test this on your own, because the GFCI, they do occasionally fail and it will be fatal. So don't do that. But anyways, that's some stuff about circuits. One thing your book also mentions right after that is, and I'm going to put it back on this earlier page. Actually, no, I'll put it here. There's something called ground that we just talked about, and the symbol for that is basically a wire and then a long bar and then a shorter bar, and then a shorter bar. Normally you have at least three. Sometimes they'll have four, five, or six, but three is plenty. Another version of that is they'll just have a wire coming into a downward pointing arrow like that. Both of those are symbols for ground. So those are my symbols for ground. You see them in the far left, and I wrote the word ground, and that corresponds to V equals 0. And what I was showing you is what I often used to do when I was analyzing circuits, when I first took a really robust engineering electronics class. Uh, I would always picture the ground being connected at the negative side of the battery. That forced the negative side of the battery to be at 0 volts. And since the battery voltage total is like 9 volts, then that means automatically the positive side of the battery is 9 volts. And if current's actually going around it, then that means technically this spot right here has to be slightly lower than 9 volts. So you might think that's 8.9992 or something like that volts. And that would be perfectly reasonable, because the resistance in the wire is so small compared to the resistance of the load that you don't expect much of a voltage change. And the symbol that I drew here, which hopefully you guys have already seen because we've had numerous labs with circuits, but that symbol is actually a symbol that we use for a resistor R. Okay. And then you know that this voltage right here is 0 volts. But in principle, since current is going around, you cannot have current unless there's a decrease in voltage. So technically, you would normally think of this voltage as 0, but it can't be 0, or else the current wouldn't continue to run around to the circuit. So you might have to call this one 0.0002 volts or something crazy like that. And then you get the pure 0 at the backside. So that's some of the stuff we try to do when we're thinking about circuits, just to give you some idea of how they behave. And I draw these bubbles all the time like this on my circuits. You've seen me do it with capacitors and resistors in the past, and that's me basically trying to show you how I think through the process. Let me see if there's something else I wanted to tell you about that. Oh, the other thing I wanted to tell you is, what is the ground? Well, if you looked at your circuit panel in your house, it would have a bunch of circuit breakers, or if you're living in an old structure, it might have some fuses, little round things that you screw in or whatever. And those fuses are more or less just flat ribbons of wire through which the current runs. But they've been tested with that particular metal of that particular size. If a current of, say, 25.2 amps goes through that, then at 25 amps it works fine. The metal gets hot and everything, but at 25.2 amps, it actually gets so hot that the thin part of the wire ribbon just melts through, and that opens the circuit. So that's how fuses work. Circuit breakers work sort of more like that GFCI I talked about earlier. It's got a mechanism where it senses a large amount of current, and when it does, it just sends that current straight to the ground. But that's what's inside your circuit panel. And if you were able to, and don't do this because there's a ton of high voltage in there and it will mess you up. But if you were able to take that circuit panel apart, what you'd see is like a big metal aluminum frame in the back. And basically all the wires are running, have a wire running to that aluminum frame, and then there's another big copper wire that runs from that aluminum frame outside. And if you tracked it, you'd find it running down the side of your house and then connected to a clamp. And then there's like about a 7/8 or 5/8 inch diameter rod that's covered in copper, and it's usually 6 to 8 foot long. Basically, the electrician took that really long rod and just nailed it into the ground until it was completely underground, and then they connected that clamp with the wire that runs to the aluminum frame inside, they attach that clamp to the top of that actual rod that's going in the ground. And that's literally what ground is. Ground literally is a connection to the ground. So, in that sense, just like we talked about in chapters 17, 18, 19, and 20, we talked about heat sinks where you could pull out as much heat as you want and it wouldn't change the temperature, or you could put in as much heat as you want and it wouldn't change the temperature of the reservoir or the heat sink. Well, the earth is like that for charge. You can think of it as a charge sink. You can add as much charge to the earth as you want, or take away as much charge from the earth as you want, and it's never going to change its voltage. So that's a way of thinking about it, and that's what we use the ground for. And when you look at light receptacles, for instance, like this, what you'll see is there is a long slit on the one side here, and then there's a short slit on the other side, and then there's this little mouth looking shape down at the bottom. That's a typical electrical socket. And what you'll see is on the side with the long one is a bright silver screw right there, and on the side with the short one is a brass screw, and it usually tells you exactly on it which goes to which. And I always forget because I don't, wire things too much. But generally speaking, if I remember correctly, the goldish colored screws are supposed to be the hot side, so that's where you connect the black to, and the silver side is what you connect the white to. And then you'll see this little green screw on the end. That's your actual ground. But you'll notice there's not only a screw on this side that connects to the long. This is the silver screw, and this is on this side is the long slit. There's not only one of those, there's two of them. And then not only that, there's actually holes in the back of the receptacle too. So you actually have three connections for that one long slit. You've got the connection of this silver screw, you got the connection of this silver screw, and then you got a hole in the back that you can plug into. And then the other side's the same way. The short side has the brass screws, so it's two of those, plus you have a hole in the back, plus another hole in the back. So technically you have like four ways: hole, hole, screw, screw, hole, hole, screw, screw. And then you only have one way for the ground, and that's what's connected to the screen thing here. But as I told you, when you buy the wire, it'll have a black wire, it'll have a white wire, and then it normally has a unhoused wire. That's the ground wire, or sometimes it might have a green housing on one, or a black house, or excuse me, a brown housing, or something like that. And sometimes you have to use that as ground. But basically, what you do to plug this in, let's say with another light receptacle, is you run the black wire from the circuit panel into, and I'm just going to trust my memory here, but I'm not actually telling you that this is factual because I'm trying to see it right now. I was hoping I could see it in real time, but I was unable to. So let me look real quick and see if I can see it. I'm trying to see if it tells me to put the black wire on the gold side or if I'm supposed to put the black wire on the white, on the silver side. Anybody know off the top of your head, any of you guys work in the electronics or in a electrician's industry? Push in number 14, copper solid wire for 15 amp branch circuit only only, and the rest is in French, so that doesn't help me. But it's got all sorts of stuff on it. So, for instance, when you look at this particular part of the receptacle, you see it's got an actual little gauge here that tells you how much wire you should strip off. You see the hole here and the hole here, and I'm pretty sure I thought I remembered the actual black side goes to the gold and the white wire goes to the silver. So let's pretend like we know that's the right answer. But again, I'm giving you the caveat that that may not be the right answer. So make sure you look it up if you ever have to wire anything. But what you would do is you take the black wire from your power supply, which is your circuit panel, and you either plug that in this hole in the back, or you plug it in this hole in the back, or you connect it with this screw, or you connect it with this screw, and then this whole side where that screw was, that all has the same voltage as that black wire. And then you want a return path for that those charges coming out. So what you then do is take the white wire and connect it to this side, either this screw, this hole, or this hole, and then that comes out of there, and that gives it its return path. Uh, Now, if you want another socket, because this actually gives you two plugs, but if you want another socket, now you'd have to do is take this other screw or this other hole and run a black wire from it to the black side of this one, which could be this screw, this hole, or this hole, and take the other side, the white one, on this first socket and run it from here into the other side of this one. So it's in that hole or in that hole or in that screw or in that screw. And by necessity, you're getting all these circuits as are all these light receptacles in parallel. And then the third wire is just the ground, and that's the one that's wired to that aluminum frame in the back. And all of them go to that one little screw in the corner of the receptacle, which looks like that guy. And they're all connected to that little hole in the bottom. So that little hole is your ground on your receptacle. You'll occasionally see, most of the time, you see your wires or your light receptacles put in your wall this way. I actually think it's a little safer and a little better to put them in this way because gravity pulls things down. And if you have a small child running around with a metal sword or a metal ruler or something like that, there's some probability that the kid's going to try to whack a wire just being fun and or having fun. And if they do, they would actually come down and could, in principle, go between the plug and the receptacle. If the receptacle's mounted this way and gravity's pulling it, then it's going to come down this way and it's going to hit this thing, which is just a ground. So there's no danger in that. That's actually quite safe. However, if you've wired your house this way and the kid does it, then they could touch the black side, which is hot, or they could touch the neutral, which is supposed to be neutral. But to be honest with you, it carries current out, so it's potentially dangerous as well. So yeah, it's a little better, at least in the kids' room or somewhere where the kids frequent. It might be better to have your receptacles put upside down. Now, another warning I'll give you about this: if you ever go to try to do any work on a receptacle, the absolute most efficient looking place to grab this receptacle when it's sitting inside of it'll be sitting inside of this itty bitty box like this, and all these wires will be back here behind it, and it's in this little narrow box that's maybe about that wide. Uh, it just feels so natural to reach right here. If you do that, it is a bad day for you. That's basically you completing the circuit. So you're taking the hot side and saying, "Hey, go ahead and go through my thumb and come on out my index finger to that white side." Or better yet, how about just go up my arm through my heart and all that good stuff. So be very careful. Do not go grabbing light receptacles by this part. You got to be very careful when the electricity's on, especially. But ideally, you don't want to work with a circuit unless the electricity is off. All right, so that's more than you possibly ever wanted to know about light receptacles, but that's something I try to teach every time. Sometimes I teach it in the first day of chapter 25, sometimes I teach it in the second day, sometimes I teach it in chapter 26. But the main thing is you just need to know this is the receptacles that we use in America. One side is positive, the other side is the white neutral, the positive being the black, and then of course the ground is the little hole at the bottom. And now I've also given you some explanations on how to do it. I could not find the instructions that I was pretty confident would tell me which side goes to the gold, but in my brain it's always been that I remembered black goes to the gold screw. All right, now that we've covered grounds and I talked about how circuits are connected, your book has exercise B. How many coulombs is 1.00 amp hours? Have you guys ever seen a unit called the amp hour? Feel free to type it if your speaker doesn't work. It looks like someone has chatted something, but that was something different. Yep. Okay, so no answers. Uh, Now I've done forgot the question. Oh yeah, with the amp hour. You'll normally see the amp hour on some of those little boxes that you see, or like independent chargers for your phone that you carry around. They're normally in amp hours, and you'll see them like in the checkout line at Walmart or something. That'll be like 10,000 amp hours or 40,000 amp hours. If you realize the amp is a unit of coulombs per time or charge per time, and then you see it's an amp times an hour, you'd realize it's charge times time, or excuse me, charge per time times time. So the time cancels out and it's purely a number of coulombs. In fact, you could look up and find out it's a certain amount of coulombs required to charge, say, a Samsung phone or an iPhone or something like that. So you can take that number, the number of amp hours that they give you on the charging mechanism, and divide that by the number of coulombs it takes to charge an iPhone, and that'll tell you how many iPhones you can charge with it once it's fully charged. So that's a good measure. It turns out, by the way, 1 amp hour is obviously 3,600 coulombs because an hour has 3,600 seconds in it. And when you multiply 1 amp, which is a coulomb per second, times 3,600 seconds, you get 3,600 coulombs. So that's exercise B at the bottom of page 721. So the next thing we got to talk about is Ohm's law, which you have a little bit of experience with. Ohm's law says the voltage is directly proportional to the current. That means if you've got a current going through a wire, maybe it's an amp, and you need 2 amps, then your first thought should be, hey, instead of using this voltage source I have, which is, like 12 lemons connected in series, like I was telling you earlier, let's do 24 lemons because if I do 12 lemons, I get, a certain voltage, but if I do 24, I get twice that certain voltage and therefore I get twice the current. So that's part of what Ohm's law tells us. And in this sense, Ohm's law is always true, period. But there are certain devices called ohmic devices. So I'll write an arrow here and say ohmic device gives you V is equal to I times R. And in that sense, when we're saying in light of an ohmic device, we're saying, hey, as long as you're obeying the specifications of this device, then that R is always going to be the same R, and V is equal to I times whatever that R is. And the way you find out what that R is you make a plot of voltage applied to that load on the vertical axis and current that goes through that load on the horizontal axis, and it'll make a straight line again as long as you stay within the specified parameters that are allowed for that device. And they normally do them in terms of power, like you can buy a resistor that's 0.25 watts or something like that, and the power is actually current times voltage. So if you actually multiply the current in amps times the volts in or times the voltage in volts, you'll get a certain number of watts. When you do that, that's the actual power that particular device is using. There's other formulas too, but P equals IV is the simplest one. So as long as you stay within that amount of power, then this resistance will stay the same, and you'll get a nice linear graph of this ohmic device's voltage versus current curve. And it's not even a curve; it's a straight line. The slope of that straight line is the resistance R. In a more general way, though, you can look at a voltage versus current graph, and it'll actually have a curve. And at any instant, for any particular current at any particular voltage, there's a single dot on that curve associated with that current and that voltage. The slope of that line at that particular current is that particular current and voltage's resistance. So in some sense, V equals IR is always true. It's just when it's an ohmic device, then R is a constant. When it's a non-ohmic device, R could vary quite a bit, like you guys saw when you did V equals I, or when you did V versus I for a light bulb. So that's some Ohm's law stuff. V is the voltage across the device whose resistance is determined to be R, which may or may not be a constant. And I is the current that goes through that device. Keep that wording in mind. Your book gives you various reminders, but voltage is something you put across a load, and current is what you run through the load. So voltage is across, current is through. Now, with that in mind, let's work an example. Example 25.3. Example 25.3 says a small flashlight bulb draws 300 milliamps from its 1.5 battery, 1.5 volt battery. What is the resistance of the bulb? And B, if the battery becomes weak and the voltage drops to 1.2 volts, how would the current change? Assume the bulb is approximately ohmic. So we have here I1 is equal to 300 milliamps. I'm going to show you that you don't have to always take off the SI prefix on these quantities when you're working, at least in electronics, it's often not used. You don't change it to amps every time. So I'm going to do that here. The voltage here is 1.5 volts, so I have 2 sig figs in this one. I'm going to assume I have 3 sig figs in the 300 milliamps. And then for part A, they want to know what is the resistance. So R is equal to question mark. And then B, they say if V equals 1.2 volts, what is I2? So that's what they're really asking here. The solution requires Ohm's law. V is equal to I times R. And normally you just lay the equation out and then put the numbers in. I often solve for the variable that I want to solve for before I put the numbers in, but whichever way you want to do it's fine. In this case, I'm going to start with part A, and I'm going to say the voltage is 1.5 volts, and that's equal to 300 milliamps. Remember, I'm leaving that milli on purpose, and I want to solve for R. So R is going to be 1.5 volts divided by 300 milliamps. Now, 300 is actually 20 times 15, and 1.5 is 15 divided by 10. So that allows me to do the math pretty easily. I can see that the two 15s cancel out, and I end up getting 1 over 10 divided by 20. So 0.005, and then I had 2 sig figs, so I put that there. And that's listed as kilo ohms. Remember, the ohm is the unit for resistance, and it looks like the uppercase Greek omega. So that's 0.005 ohms, but that's in kilo ohms. So to make it into ohms, I just move the decimal 3 places to the right, and we see that we get 5.0 ohms is equal to R, and that's part A. So again, this was me showing you that you don't always have to convert your millis and micros and nanos and kilos to the base unit. You can sometimes use it. You just have to think it out a little bit. Now, for part B, they want to say, what if the voltage goes to 1.2 volts instead of 1.5 volts? And pretend the resistance stays the same. If that's the case, then you got 5.0 ohms times I is equal to 1.2 volts. If I solve this for I get I is equal to 1.2 volts divided by 5.0 ohms. I do encourage you guys to think of ways to do this arithmetic in your head because it's better for your brain, and it's also likely to keep you from making careless mistakes. But I'll just do the calculation here so it don't take much time. So when I do 1.2 divided by 2.5, 5.0, I get 0.24. And that's an extra digit there that's not a sig fig. A volt divided by an ohm is an amp, so this is actually equal to 240 milliamps is equal to I2. So what we just discovered here is that if the battery starts to die and no longer has that nominal 1.5 voltage, which I've mentioned before, and I'll mention it now, AA, AAA, C, and D batteries are all nominal voltages of 1.5 volts, but when you buy them, they usually will measure somewhere between 1.68 and 1.73 volts. But over time, as you use them, that measurement gets smaller and smaller. Once it starts to get in the 1.5 range, that's when your battery's starting to get so weak that you're not going to be able to use it much longer. If it doesn't matter that it spins, half as fast as it did when it was with the fresh battery, then by all means use it till it gets down to 1 volt if you want. That's fine. But if you have something that really needs the appropriate amount of power going to it because it's important, then yeah, you want to throw those batteries away once they get lower than 1.5 volts. Any questions on example 25.3? They do talk about resistor codes. They have a nice picture of various resistors where you see like this big figure 2511. There's a big resistor that has two orange stripes, so it goes orange, orange, brown, red. There's a couple more in here that go green, or no, I don't know if that's green next to brown, next to black, or if the line's black or if the line's green. But there's a lot of different colors, and they even tell you the first digit is the first line, the second digit is the second line, the third line is the multiplier, like 10 to the fourth. The multiplier would be 4, and then the fourth line is the tolerance, so it's plus or minus 5%, plus or minus 1%, that sort of stuff. And they even give you the resistor color code. And again, if you speak to some of your Navy folks, you probably find that they have some useful mnemonics for memorizing that. But I will warn you that the ones that I ran into were largely uh, a little, sketchy. It's a little sexist and a little sketchy. So just remember that that's a possibility, and be advised. You might want to make up one that's not chauvinistic or whatever. So now let's go to conceptual example 25.4. Basically, what they have, they say current I enters a resistor R as shown in figure 25.13. I'm going to draw a figure like that in a second. A is the potential higher at point A or at point B, and B is the current greater at point A or point B. So the diagram they have, I'm going to go ahead and draw another line here to separate this from the next problem. This is example, and it's conceptual example 25.4. And what we have is a wire, and then it runs into a resistor, and then it runs out like that. And they have here the point A, and they have here the point B, and then they have an arrow drawn this way, and that's supposed to represent the current, and an R down here is supposed to represent the resistance. And part A says, is the potential higher at A or B? Does anybody know the answer? Is the electric potential? Notice when they just say potential, they mean electric potential. And that's different from electrical potential energy because that's something you measure in joules. When they say electric potential or just potential, they mean volts, and that's a joule per coulomb. So Alex has told me that he believes the potential is higher at A, and that's absolutely the truth. In order for a current to flow, it has to flow from high voltage to low voltage. So for part A, voltage at A is greater than the voltage at B. That's the whole thing that makes the current go at all. If there's no voltage difference, you're not going to have current, period. No ifs, ands, or buts about it. Okay. Now, the other part they want to know is B. I'm going to write it over here in blue. B, they want to know, is the current greater at point A or point B? Now, remember, current is a flow of charges through the wire. And if, for instance, 100 coulombs came into point A in a single second, unless you violated conservation of charge, because there's no extra paths for the charges to go through, that means that 100 coulombs have to come to B every second as well. So I at A has to equal I at B because of conservation of charge. Because remember, these are charges moving like from left to right. So in order for us to not have it, you'd have to have something like, okay, here's A, and then here's my resistor, and then here's B. In order for you to have a different current at A than at B, you'd have to have like another wire coming out here or something like that so that some of the charges can go down and some of the charges can go to the right. Then IA could be different than IB. But if you don't have a node, that's what this is called, is a node. If you don't have a node that allows an alternate path for the charges to go through, then the currents have to be the same. That's why the currents are the same in all items that are connected in series. So if you have, 84 resistors in series, everyone's going to have the exact same current going through it. But that also limits our definition of what series is. So for instance, that what we see here in the second diagram, that's no longer a series type of circuit. If I put a resistor right here, that's neither in series nor parallel. I'd have to draw the rest of the line to figure out if it's actually parallel, but right now it's neither series nor parallel. Any questions on that? Your book does say, caution, voltage is applied across a device, current passes through a device. Caution, current is not consumed. So that's another thing to talk about. Now, I want to get into resistance, and I think it makes some sense for you. I'm going to draw a couple of diagrams. So if you imagine trying to, let's say this is a tunnel instead of a wire. Let's say you have a tunnel here and you're trying to evacuate some elderly people from a retirement home, and you have two halls that you could use, two tubes, if you will, that you could use, and you want to figure out which hall is going to allow you to get the uh, elderly people through the fastest, or which one's going to make it slower. Can anybody tell me if I try to send people in here and out here, or in here and out here, which one's going to be more difficult to get the elderly people through? Which tunnel is more difficult to move the elderly people through? And Alex said the top, and he's right. So that tells us the difficulty, which I'm calling resistance, is directly proportional to the length. So the top is the answer. So R is proportional to the length L, and I'm calling this L, and I'm calling this L2, and L is longer than L2, so the long wire is more resistive. The other thing is, what if I had this tunnel, and I should break these off so we don't confuse the questions as being related to the same thing. So I have this tunnel, and then I have this tunnel. Which is more difficult? Yes, the bottom would be more difficult. It's a little harder to see with elderly people because you can't really use the extra height. But we can imagine this is the International Space Station, and we're throwing them through like little torpedoes in a pool or something. So yeah, in this case, the bottom, and that means that the resistance is inversely proportional to the area, meaning a large area makes for a smaller resistance. Now, we have two variables that are involved here, and what we do to switch from a proportionality to an actual equation, from algebra 1 and pre-algebra, what you have to do is add a constant. But one thing we haven't taken into consideration is, what are those tunnels filled with? If it's just air, then yeah, both of them being air is not a problem. The elderly people can get through it. But you could fill one with air and you could fill the other one with jello. So if you're thinking about a hall filled with jello, that's going to be a problem. So to take that into account, what we did is we make the constant into a constant that depends on the material, and that also includes the regular constant as well. So the formula that we actually work out is that R is equal to the resistivity. That's the variable rho there. It's called the resistivity, and it's rho times L over A is the formula, and that's the formula that tells you how resistance is related to the material through the constant rho, and the length or the geometry of the wire, which is the length L, and the area, which is also part of the geometry as well. And can anybody tell me, based on this equation, what you think the units of rho will be? This is something you should be able to do as any student that's this far in their 241, 242 sequence. You should be able to readily tell me what the units of rho would be. Remember, R is in ohms, which we've already been working with in lab. So there's the ohm. Can anybody tell me what the unit of the L would be? So this is how you work it out if you can't see it in your head. Uh, we see the R is in ohms. We see the rho is what we're looking for. The units of the L is meters, and the units of the area is meters squared. So you can immediately see that the exponent of 2 is going to cancel out up here. And if you actually solve for rho, then you get the units of rho are equal to ohms times meters. And that's right. And then table 25.1 gives you a list of those values. For instance, copper has a resistivity of 1.68 times 10 to the negative eighth ohm meters. So that's one piece of information. But they also have alpha, which is called the temperature coefficient of resistivity. Uh, And you probably remember this equation in terms of lengths, but in terms of resistivity, it also works. Uh, Here's the other equation that you can use. I just want to give you these equations so you can get started on working. The resistivity at rho is, or excuse me, at a temperature T is equal to the resistivity at a temperature T0, which I just subscript O, not T0, times 1 plus alpha times t minus t0. That looks just like the equation that gave us the length of a piece of metal or something is equal to the original length times parentheses 1 plus alpha t minus t0. The A similar equation can be gotten for the resistance, and you write that as RT is equal to R0 times 1 plus alpha times t minus t0, like that. So these two equations you'll need as well. And those are the types of examples I'll work next time. I don't feel like we're bad off because I wanted to get through that stuff about the light sockets and all that good stuff. So we've got that done. But you can readily start your homeworks on this now. And you can also start looking at any of my other videos. Do searches for resistivity, do searches for temperature resistance, resistance and temperature or something like that in my YouTube channel, and you'll find plenty of videos. But we're done. You guys are free to go. I hope you have a nice weekend. Remember, we're going to have a face-to-face test that'll be due sometime next week. Basically, you'll be able to take it as early as Tuesday, and then I'll allow you up until at least Tuesday of the following week to get it done. I'm planning on offering two proctoring sessions with me the week after. So I'll probably offer like one on Monday morning and then one on Tuesday evening or something like that. So try to make a schedule for that. I should send out an email today or tomorrow about what those times are. I'm having a hard time deciding which ones I can fit in, but I will be doing that. But you can also make your appointments at the testing center for any day, including Monday, even though I said Tuesdays when is the best one to start. But you can set up your test for your second face-to-face test as early as Monday and as late as Tuesday of not next week, but the week after. Have a good one. I'll wait for the last person to leave in case anybody has any questions, but thanks for coming. The way to think of an ohm is remember a volt is a joule per coulomb, and an amp is a coulomb per second. So you've got, if you're talking about Ohm's law, for instance, you have uh, V equals IR. This would be a joule per coulomb is equal to a coulomb per second times an ohm. So if you wanted to actually solve for the ohm, you could see that the ohm would be a joule second per coulomb squared, and that might be what you found was something trying to say that, but they might have put a dot between the J and the S, and it became a negative instead of a dot. That could have been what it is, but that's what that's a way of looking at a ohm is a joule second per coulomb squared. Of course, you remember a joule is a Newton meter, so it could be a Newton meter second over a Coulomb squared. That's another way of looking at it. I like to think of it just as the ohm is equal to a volt per amp. That's the way I like to think of it.
Cool. That makes sense.
Yeah, just use your algebra to lead you there. And there's actually, over time, we've changed things. Like, at one time we considered the coulomb as the fundamental unit, and then later we made the amp as the fundamental unit so that we have a test for that the International Bureau of Standards has put together for us to determine what 1 amp is. In that sense, it's kind of weird because we always looked at the amp as a coulomb per second. The second is a fundamental unit, and we thought of the coulomb as a fundamental unit. But by doing it this way, now we think of the amp as a fundamental unit, and the second as a fundamental unit, and the coulomb as a derived one. So it all depends on what perspective you're looking at. Does that
Cool.
make sense, Alex?
It makes sense.
Yeah.
Um, and I do want to ask one question about the testing.
hmm
So I understand that you're going to proctor it, and there's the testing centers. Are we not doing the Zoom?
Yes, my proctoring would be a Zoom proctoring. That's what
Oh,
I'm referring to. Yeah, you can still come
okay.
to my class and do it, but that would be Wednesday of next week, and very few students show up for Wednesday of next week. But you're welcome to. Otherwise, you're going to have a setup where you have a cell phone, uh, running Zoom and has a camera that can watch you, your computer screen, your workspace, and you can also use that camera to show me your whole room, show me the doors closed, leave the volume on all that time. Might even need an additional mirror, but the main thing is you could do it via Zoom and I could monitor you that way. So that's what I was talking about when I said Tuesday and Monday of the following week.
Okay, that makes a lot more sense. Yeah, because usually Wednesdays I have some class.
Yeah, what I'm going to do is offer, like, you could come to my class, one of my classes on Wednesday, which would mean you could do either the 12:20 to what 2:50 or something, or yeah, 2:50 or something like that, or you could do my 2 o'clock to 3:20 class, or you could do one of my online proctoring, which would be like 7:30 in the morning, or another one at like 7 at night.
Yeah, usually the night classes work out for me because I also I work 4 days a week in the
Gotcha.
morning usually. But I appreciate it.
No problem.
Th-
Have a good one, Alex. Start working on some homework problems with these last two resistance formulas, and that'll help you. But I'll show you some examples next. So if it's not that crystal clear to you, don't worry about it. That sometimes happens. You'll get there once I teach it to you.
Oh no, it totally makes sense. I guess I trusted the internet a little too much, I guess.
Most of the time, I do find the internet's pretty good on physics. It's Wikipedia can be kind of bad sometimes because you get some crazy people in there with some alternative hypotheses and alternate realities telling stuff. But most of the stuff I've found on Wikipedia is correct. It's just every now and then you'll find one really glaring thing. Or the other problem is, like, I suspect what you found with that ohm was probably a typo more so than someone not putting it up correctly.
Yeah, I mean it's nice that people can edit Wikipedia pages, but I wish they had a license for it.
Yeah, it's nice to have it publicly watched for, and there are people that do that. They spend their whole life doing that, and it's free. I mean, they do it all for free, so you've got to, give them a little bit of credit for being willing to help the whole world by their own work. I've done a little bit of that. They call them the Wikipedia gorillas or something like that. I remember on Skepticality, they had a couple groups together that they would do it for Skeptic Magazine. So most of the stuff is pretty good, but every now and then someone will come in and type some BS up there because they believe it, and they're not, more than likely they're not trying to be liars, but in some cases they might be. It's just a matter of they're a little confused, but luckily if you wait long enough, someone will come in and correct it.
I mean, that makes sense, like guerrilla warfare, but for intelligence.
hmm Exactly. Yeah, I forgot the name because I actually did a couple projects with them, and then I completely forgot. I haven't. That was like 15 years ago. So
Well, again, thank you so much, and I'll see you Tuesday then.
no problem. Sounds good, Alex. Have a good weekend, bud. Stay
You
safe.
too.
Bye bye. A lot easier. I can say bye bye.